for vice president. So student membership in the Society of Rheology, $25 a year, very reasonable. Full-size professional membership, $40 a year, also very reasonable. So take a look. All right, we're ready to start. I want to start today with a little bit of I forgot in my excitement with this new method of delivering class, I forgot my usual technique, which was to review a little bit every day of what we talked about last class. And our goal right now is to learn to do these mathematical manipulations. So we're going to be doing a bit of work on the board essentially today to try to gain some familiarity, to make it easy to do these kind of calculations. So what we talked about last time was the definitions of the various mathematical entities, the scalar and the vector, and the commutative, associative, and distributive laws. And we were going to see that as we manipulate our expressions in Einstein notation, it's going to be really important what's allowed to commute and what doesn't commute. Because vectors within that indeterminate product, which is tensors, do not commute. Scalars commute all over the place. They can go anywhere. And everything distributes. So these laws that seem perhaps a little bit esoteric, a little bit, you learned them actually probably in algebra class a million years ago, and they haven't seemed that important after you memorize the easy ones, but they're important again because we're essentially learning new algebra. With vectors, we learned that there's magnitude and direction. This magnitude is a scalar. This direction is a vector, and we're going to often be separating them out. And we're going to see also that when we use Einstein notation to do these kinds of additions and subtractions, that we're going to manipulate the coefficients and let the vectors add themselves. So we'll see a little bit of that. And then we're going to see, as I said, this commutative and distributive laws for vectors. We're not going to use the cross product too much. And then coordinate systems. So I've already talked about the homework that's related to this problem. Anybody have any questions about showing that something's a basis? If you have a question and you're too shy to ask on tape, I can answer questions after class as well. And then Einstein notation. So remember, we introduce coordinate systems because we want to do actual calculations. So real-life calculations mean that our equations have to be rendered in a very particular coordinate system. So we render them in a coordinate system, and when they're written in a coordinate system, there'll always be the coordinate vectors either very explicitly written or implicit. Okay, this subscript xyz here on this column vector says this is just a way of organizing the three coefficients of the vector A with respect to a particular coordinate system. If I change coordinate systems, these numbers change. And I'm very explicit with what coordinate system I'm talking about. A lot of books aren't, and I think that's why people end up a little confused sometimes. But I'm always going to be very explicit as to what coordinate system they refer to. Because we're not always going to write everything out. So for instance, this is the formal way that says that any vector may be written as a linear combination of three non-coplanar, non-zero basis vectors. That phrase is stuck in my mind. I'm trying to stick it in your mind. And once we've done that, we can write it in this contracted form and then eventually in the Einstein form. So skipping ahead to the Einstein form of a vector A, the Einstein form is, this is very familiar to us, so we can write it as this summation 1 to 3, or leaving the summation out as just the repeated indices A sub j, E sub j, or A sub m, E sub m. Okay, that's the Einstein notation, and the key thing is how to use that in doing dot products. It works with dot products because these are an expression for use in Cartesian coordinate system. The Cartesian coordinate system has two properties. One, it's a orthonormal coordinate system. The second is it's a constant coordinate system. Once you've chosen the location of the origin, the direction that is z doesn't change. Everywhere in space, up is z. Z is up here, z is up over here. Everywhere, x is one direction and z is the other. There are, in this spherical and cylindrical coordinate system, you're familiar with, let's say, the cylindrical coordinate system, actually the directions change. So if this is the cylindrical coordinate system, if I locate myself at this point, the direction r is outward at this point. But if I'm over here at this point here, P2, or P1, I guess, the direction in r direction is that way. Okay, so in this coordinate system, when you have ER, E theta, EZ, in this direction, this is the direction of ER. At this point, this is the direction of ER. So these depend on location. Z does not. Z always points up, but theta also depends on location. So depending on the point you're talking about, the direction of the coordinate basis vectors is different. And that's going to give us indigestion when we start doing derivatives. That's why for our Einstein notation, we limit ourselves to the Cartesian coordinate system. X is always this way, x is always east, let's say, and y is always south, and z is always vertical, period. Okay? We can pick different Cartesian systems within one problem, but different points in space, that coordinate system is exactly the same. That's going to be nice for us, and that's why we do it. So the orthonormal part allows us to replace any dot product of two basis vectors, EI, EP. So these are representing different values of EI, EP within a double summation. And they're either this dot product is either 0 if they are perpendicular to each other, which is when I is not equal to P. And it's equal to 1 when they're parallel to each other, which is when I equals P. So E1 dot E1, E2 dot E2. So let me do that one more time as a review. We're going to see this a bunch of times today. The idea behind Einstein manipulations of two vectors, let's say v dot w, is we write each vector with respect to a Cartesian coordinate system. So that's v, I, e, I. And every new vector gets a new letter. Dot w, p, e, p. What letter we pick is irrelevant. Okay? We dot the two basis vectors together. The scalars commute. So usually I take my scalars out front so I don't get confused. And the dot product, as we saw from the notes, the dot product of two unit vectors, EIEP, is equal to the Kronecker delta IP. And I read that as I becomes P. So if I becomes P, then this must be VP, WP. That's my final answer. And then the Einstein notation rule is when there are duplicated subscripts, there's a missing summation sign. So that means there's a missing sum. This is equal to the summation P equals 1 to 3 of VP WP, which is the answer we thought. V1 W1 plus V2 W2 plus V3 W3. I'm running out of space here. Now, let's talk about the next level of complication, which is the tensor. Okay. So I gave a little bit of intro about the tensor last time, and now I'll give it to you a little bit more formally. The tensor, the definition from a mathematical perspective is that it's the indeterminate vector product of two or more vectors. And the stresses that we're going to the tensors we're going to care about are the stress tensor, the velocity gradient tensor, and later various strain tensors. Now, tensors may be constant or variable. That reinforces what I was saying about scalars, and vectors can be constant or variable as well. Okay, so we're going to see tensors written two ways. This stress tensor way is the single symbol method. So that would be like this arbitrary tensor A double underbar here. And this AD method is like writing this indeterminate vector product. So two vectors sitting next to each other are the indeterminate vector product of A and D, and this is called the tensor dyad. So because this is a vector product, just like the scalar vector product and the cross product, it's got rules. And this is the key rule right here. It is not commutative. Okay? AB, AV is not VA. On the previous slide, AD is not equal to DA. E1, E2 is not equal to E2, E1. Okay? That's the most important thing to remember about handling these quantities. The good news is it is associative. If you have three tensors multiplied in an indeterminate way, three vectors multiplied in an indeterminate way, they associate like that, creating a third order tensor. You can either implement AV first or BA first. BV is irrelevant. B and V are not next to each other, so there's no BV tensor here. But there is an AV second order tensor and a BA. Also, they distribute. So if you add two vectors together, but then they're in the indeterminate vector product with another one, you can distribute them. Let me stop for a second and go back to saying why we might need something that has two vectors. If you think about stress, stress is our favorite tensor. Why is stress a tensor? And we can just sort of get some sort of physical idea why stress is a tensor, again, by leaning on the table. Okay. So this table has an orientation. The surface that I'm choosing to put a stress on is this top surface here. And then I'm leaning on it. So when I ask the question, what's the stress on this surface? There are two vectors involved in the question. One is, which surface are you talking about? Well, I'm talking about the surface whose unit normal in this case is Z. And then what's the direction of the force? Well, the force is this direction of my arm pointing downward on the table. Now, my arm, me leaning on this table, is also putting force on other surfaces inside the table. Okay, I could think about some surface perpendicular. If this table were made of jello, something very soft, all right, and I push on it, then we know that it's going to deform a little bit. So there are forces transmitting to the inside of the table. They're transmitting to the inside of this solid table too. It's just a little bit harder to visualize. If you visualize it a little bit softer, you think, yes, this leaning, if it were jello, would certainly be putting some sort of force on the inside. So to ask a question like, how much force is there on a plane that's parallel to this wall inside the surface, you have to tell me what surface you're talking about. And then I'm going to answer you what force I'm talking about. Two vectors. What plane? To define a plane, you have to give a unit vector normal. What force? That force on that plane could be pointing in any direction. This one I'm putting on is a little bit down and a little bit in. So if there's let's say that's the x direction, a plane of unit normal x has a force that's in this crazy direction, two vectors. So that's just some tickling of an idea of why these things turn out to be tensors. The reason is because we want to summarize into one mathematical entity the state of stress at a point. The state of stress at this point. What's the stress at this point? Well, that's not really well defined. You have to say this plane, and then I'll say, oh, the stress is that way. Okay, now this plane, oh, the stress is that way. How about this plane? The stress is that way. You have to always say what plane, what force, what plane, what force. So to define the state of stress at a point, you need a function that when you tell it this plane, it will tell you that force. That's a linear vector function, as it turns out, and that's what a tensor is. It's a tensor that when we start dotting things to these tensors, they're going to, when we dot a vector that's for, say, this plane, it's going to tell us what force, if the function is well defined. So that's not going to be crystal clear at this point, but maybe just a little motivation for why we're dealing with these higher order entities. All right, so now how do we render something like this indeterminate vector product in Einstein notation or in even regular notation? Let's start by writing a little bit. If I start with this AV, indeterminate vector product, we actually already have these commutative, associative, and distributive rules, so we can sort this out. And I already flashed up the nasty answer. It's a big, nasty answer. But it's a little bit more intelligible if we take it in little chunks. We can do the same thing that we did with dot product and write that any vector may be written as a linear combination of three non-zero, non-coplanar basis vectors. So I've got AE plus AE plus AE. These are my three basis vectors. 1, 1, 2, 2, 3, 3. Okay, that's A. If I put it next to V, also written in the same coordinate system, V1, E1 plus V2, E2 plus V3, E3, I have correctly written my tensor. If I go back to my slides, I know that I may not commute, but I can distribute. I can distribute. So now I'm going to distribute this. If I have this A1, I've got kind of a complex distribution here, but just like I was going to multiply these out algebraically, I'm going to associate this one first with that, second with that, third with that. So that means, you can see there's going to be a lot of terms here. I have A1, E1 now sitting next to V1, E1. And then I have A1, E1 sitting next to V2, E2. And I have A1, V3, excuse me, A1, E1 sitting next to V3, E3, etc. So I showed you this last time. It distributes. The commutative law of these coefficients, these scalar coefficients, allow us to pull those out. And so that allows us to simplify. And what we end up having are 9 terms. 9 terms. And now I'll switch back to these slides. 9 terms where each combination is represented. 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. I'm not going to combine 1, 2 and 2, 1 because, no, they don't cancel. Because they don't commute. Okay? 2, 1, these E1, E2, in that order must stay in that order. E2, E1 in that order must stay in that order. So these are 9 separate coefficients. Nothing simplifies at all. The only thing we can do to make this more organized is to put it into a double sum. And it is organized in the sense of the double sum because the coefficients of see, when I distributed these were all 1. 1, 1, 1. And then I distributed this one, and there was a 2 on the left side. And then I distributed this one, and there was always a 3 on the left side. So it's the same thing as if each time I went 1, 2, 3, I was summing, let's say, k from 1 to 3 for w equal to 1. Okay? W was equal to 1, and then k was equal to 1, 2, 3. Then w was equal to 2, and then k was equal to 1, 2, 3. And w was equal to 3, and k was equal to 1, 2, 3. So there's our double sum. So the rule for vectors was any vector may be written as a linear combination of 3 basis vectors. And the rule for tensors is that any tensor may be written as the sum of 9 dyadic products of the base vectors. So there's the 9, and they don't simplify. Now, if I have a vector that's not written as AB or VW, something written as A double underside, we can still say that A can be written as the summation of 9 dyadic products. So we can skip right to the double sum notation, again using arbitrary indices. In this case, I used I and J. And as we did with vectors, we just drop the summation signs and just write them bare, because doing this more than once or twice, it becomes very convenient to be just a little bit more compact. So now it's time to start to do the kind of calculations that we've been aiming at, which is to use these vectors, these tensors, to make combinations that'll be useful to us. And that involves this dot product. So let's try some of these, and I'm going to ask you to help me out. So just when I call out, I hope you'll shout something out. So let's try one. Let's try that second one, A dot UV. Okay, so this is a tensor. It's a dyad. This is a vector. And we're dotting them together. So I'll show you how we do this, and then you're going to help me do the next one. So we're going to write it in Einstein notation. And to write a vector in Einstein notation, we just write A, P, E, P. Okay, that's the summation P equals 1 to 3 of A, P, E, P, and we're not writing the sum. We write the dot product. And then we have the next thing to write is a vector, which comes out exactly the same. Okay? It's U, E, and I'm not going to pick P. I've already used P. That summation's been used, so I pick something else. Let's say I. So this dot is getting bigger here. I keep trying to make it circular. There we go. That's the dot. And then no dot, the VE. We need yet another letter. Let's do J. VJ, EJ. So that's writing the expression in Einstein notation. And the only thing we can do to carry it out is to carry out the dot product. The dot product acts between the two neighboring unit vectors. It has no effect on anything that it's not right next to. So this is the dot product between EP and EI, and that's going to give the Kronecker delta. In other words, when I take this dot product, it's 0 when P is unequal to I, and it's 1 when P is equal to I. That's what this Kronecker delta notation is doing for us, simplifying that logic. We could write them all out, 9 terms, and then we could go through and take the 1 1s, the 2 2s, the 3 3s, and throw out the 1 2s, the 2 1s. That would be very boring. Okay, so this idea behind this nomenclature is to make things simpler. So now I have AP, UI, VJ, delta PI, and EJ. Delta PI I read as P becomes I. You can read it as I becomes P. It's irrelevant. I just pick one way and stick to it. P becomes I everywhere I see it. Okay, so there's a P up front here. It becomes I. This is already u sub I. That stays. J, what do I change j to? Nothing. We leave it as j. It doesn't say to do anything, so we don't do anything. And ej. Okay? P becomes I. Now, that's the final answer, but now we have to recognize it. Okay? Let's start by asking the question, is it a scalar, a vector, or a tensor? Why is it a vector? D.
So the first three is a scalar.
Right. The first three items are a scalar. And this last one? Vector. So it looks like a vector to you. Yeah. It's a vector. Now let's put the summations back. Then we'll see it more clearly, right? Everywhere there's a double summation, there's a missing sum sign. Okay? So there's a missing sum over I and over j. There's no more p. Right? Where did p go? When we dotted these vectors together, some things went away. Right? Every time we dotted E1, E2, it went away. E3, E4, E1, it went away. And when they went away, we lost a bunch of terms, and that's where that summation went. So let's put the sums back. I'm going to bleed on to another slide halfway up here. Okay, good. Now we'll put the sums back. Equals summation I equals 1 to 3. Summation j equals 1 to 3 of ai, ui, vj, ej. Now, that's still a little bit hard to understand. Let's carry this I summation out, because it has nothing to do with the vectors. Okay, so let's carry that one out. So this is a1, u1 plus a2, u2 plus a3, u3. That's just a number. You know, if A had been 1, 2, 3, and U had been 4, 5, 6, then A1, U1 would be 4, A2, U2 would be 10, A3, U3 would be 18. We'd add those three numbers up, we'd just get some number. So that's just some number. And then we're still left with the summation j equals 1 to 3 of vj, ej. That looks awful lot like a vector, right? In fact, that's the original v vector. It's completely unchanged, except it's now been stretched by this number, which I can't do in my head, 18, 28, 32, okay? So for my example, it's 32. So my answer of a dot uv was some number, a dot u, that's just some number, it turns out to be 32 for my example, times v. It's a vector in the direction of v stretched out by multiplying it by 32. That's what this final answer is. And so if I wrote this in column vector form, I could write it as, I don't want to write that 3 times, I'm too lazy, so I'll go back to a I, ui, I equal 1 to 3 times v1. That's the 1 component. Summation I equals 1 to 3 of ai, ui, v2. That's the 2 component. Summation I equals 1 to 3 ai, ui, v3. That's the 3 component. That's the answer for a dot u v, written in the 1, 2, 3 coordinate system. So looking back up here, this j sum, because it's linked to the unit vectors, this is j equals 1, this is j equals 2, this is j equals 3. This I summation, it just entirely gets carried out. It's just a bunch of numbers. Taking this tensor and multiplying it by this vector gave us a vector in the direction of this second vector that's part of the tensor, stretched by this front piece here. Okay, so let's try it with the double underline notation. B dot A. How do we start this?
Is there a way we can split up A?
When we write it in as, if I go back over here to the slides, when we write it like this, we're essentially splitting it up. So once we write it in Einstein notation, it'll be clearer how to do the multiplication. We can't immediately identify that v, you know, that second vector. But when we're done with the calculation, we'll know exactly the direction of the vector that results. Because this is also going to give a vector, right? Because it's the same thing as the previous calculation. A vector dotting a tensor is going to give a vector at the end. In the case of the previous one, we could tell the direction just even before we started with a little experience. Now we can't tell the direction. But when we're done, we'll know the vector itself. And so if we wanted to, we could identify that vector. So do you know, how would we start writing this? How do we write a vector b in Einstein notation?
Bj.
Right?
Ej.
Right. Bj, Ej. Put the dot in, and then how do we write the tensor?
The A and then subscript
Yep, pick some.
L
Okay.
and M.
LM.
E, L, and EM.
Correct. Okay, as long as we pick different ones, we can pick anything we like. And depending on how neatly you write, there may be some letters that you're better off using and some that are confusing for you. Okay, so it's up to you. I have no opinion. You may eventually run out of them in some complicated calculation, but it's fine with me as long as they don't confuse you. Okay, and so now it's the dot product of the two unit vectors that are closest together. So I usually, as I said, I usually collect all of the scalars out front just to keep myself from being confused. And at the beginning, it's not a bad idea to just recopy what's going on here. So there's no dot in between here. There is a dot here. So this is EJEL. And what does that dot become? If I go back up on the slide, oh, it's on the previous one. Like this. This is what we're doing, right? So what do I write?
Delta JL.
Right, delta J L. So we read that as J becomes L. Because we don't need J and L. This delta JL goes to 0 whenever J and L are not the same, so we don't need them both. So we pick, I'm left-handed. I picked the first one. Or actually, I picked the second one, so I guess that's not logic. I always keep the second. Okay, J becomes L, so this becomes B.
L.
L. This becomes?
L, M.
Right, no change. This becomes? just becomes 1. Because it's 1 when j is equal to L, and it's 0 otherwise. The zeros are when we're getting rid of the L. J becomes L. This just goes away, becomes a 1, which I don't usually write. And then EM stays. Okay, is that a vector, a tensor, or a scalar? Why?
BL and KLM are scalars.
These are scalars, and there's one unit vector. There's a summation over M. That's going to give us E1 plus E2, E3 with different coefficients. So yes, this is a vector. Okay? There are two missing sums. There's a sum over L and a sum over M. The sum over M is going to give us E1, E2, E3. The sum over L is not going to affect that, but it's going to affect the coefficient. So let's put them back in. Summation L equals 1 to 3. Summation M equals 1 to 3. A, L, M, E, M. Okay, we can carry out, let's try carrying out the M one first. What happened to B? B is right there. Sorry. Thank you. Okay. Let's carry out the M summation. Okay? So I'm gonna leave the L one in. Summation L equals 1 to 3. And now B L A L, but first I'm doing M equals 1. So it's A L 1 E1 plus, and then everything again. Summation L equals 1 to 3 B L A L 2 E2 plus summation L equals 1 to 3 B, this has to be an L, that's why I have to be a little careful with my L's and my 1s. BL. BL AL. Remember this, I'm doing the M summation. All right, M is now 3. Now we can see it's a vector. This is the 1 component. This is the 2 component. This is the 3 component. If I ask the question, what is the coefficient of B dot A in the 2 direction? Do you know what it would be? What? It would be this, right, it would be this mess here. It's the stuff in front of the E2, okay? And if we wrote that out completely, the answer would be, we have to do the sum, L equal 1 to 3. So it's B1A1 2 plus. Now L is 2. B2A2 2 plus. Now L is 3. B3A3 2. That's the coefficient of B dot A. B dot A in the 2 direction is this. Here's L equals 1, 2, 3. Everything in the 2 direction has a 2 in this second location on the A. We can get more complicated than this. We can dot 2 tensors together, for instance. Let's try that. How shall we start?
Separate them out into their sum.
Right. So we do that by going A,
F, O,
F, L. Okay? A, F, L.
E, F, F,
Right?
then B, I, K, E, I, E, K.
Mm-hmm. Now?
Could you move the coefficients?
We can do that. A, F, L, B, I, K, E, F, E, L, dot, E, I, E, K.
And then you can do the delta Li.
Right, delta Li. The two that are next to each other are the ones that operate. And so L becomes I, which is merciful because having both an L and an I is a little confusing. Okay, so L becomes I. So what do I write? A sub
Fi,
Fi, B sub
Ik,
Ik,
E sub F,
EF,
Ei. Well, no, that goes to 1. And Ek.
EK. Right. Very good. So that's having done that without ever having seen it before. So very good. What did we get? Did we get a scalar, a vector, or a tensor? We got a tensor, right? It looks just like this starting material. This is a confusing coefficient, but we just have two unit vectors side by side. So that's a summation. There's going to be 9 dyads, 9 unique dyadic products here, and that's just a tensor. So what are the tensor coefficients? Well, we got to put the sums back in. All right, we have a summation over, we have an F summation, there are 2 F's. We have an I summation, there are 2 I's. And we have a K summation, there are 2 K's. Okay, so we have 3 sums. Summation F equals 1 to 3. Summation I equals 1 to 3. And summation K equals 1 to 3 of AFI, BIK, EF, EK. There's 27 terms there. 27 terms, but there are 3 E1, E1 terms. There are 3 E1, E2 terms. There are 3 E1, E3s. So there's only 9 dyadic sums. I don't have to go through, add them all up. I can just do the one sum that does not involve the vectors, and I'll be able to see what the coefficients are. So which sum does not involve the vectors? I. The one that involved the dot product. Correct. So let's carry out the I. All the others will keep. Summation F equals 1 to 3. I we're going to carry out. Summation K equals 1 to 3. And everywhere we see an I, we're going to put a 1. Okay? AF1, B1, K, EF, EK. Plus. We're carrying out a sum, so now there's going to be a sum between the terms. Summation F equals 1 to 3. Summation K equals 1 to 3. AF2, we're now at I equals 2. B2K, EF-EK. Plus. Summation F equals 1 to 3. Summation K equals 1 to 3. AF3, B3K, EF-EK. That was the I equal 3 term. So now if I would look and say, what is the coefficient of the 2-1 component of A dot B? What's the answer? It's tricky. The 2-1 component is all the terms that have E2, E1. What does F have to be? Okay, F is going to be 1, 2, and 3. F is the coefficient of the first E, so what does F have to be? 2, right? K is the coefficient of the second one. We're looking for the 2-1 component. What does K have to be? Right. So all we have to do to answer this question is F equals 2, K equals 1. Okay? We don't have to do the sums. The sums give us the total answer. We're just asking for one particular coefficient. So when F is 2 and K is 1, there's a 2, 1, 1, 2 here. When F is 2 and K is 1, there's a 2, 2, 2, 1. When F is 2 and K is 1, there's a 2, 3, 3, 1. These three sums are kind of redundant, right? I mean, we could just write the summation once. Like that. And we could even factor that EF, EK out. Let me do that. A dot B equals, let's just write this in a more smooth way. AF1 B1 K, and then times EF EK. I'm factoring out the EF EK. Plus AF2 B2K times EF-EK plus AF3 B3K times EF-EK. Kind of wrote that in an awkward way even after I tried to make it cleaner. Okay, so what is the coefficient? F equals 2, K equals 1. F equals 2, K equals 1, F equals 2, K equals 1, F equals 2, K equals 1. The summations don't matter anymore. A sub B21 is equal to A21 B11 plus A22 B21 plus A23 B31. So I said there were three terms that were in front of each dyad. This is the coefficient of the E2, E1 dyad. And these are the three terms that were in front. And they add up, and that gives the coefficient, the 2, 1 coefficient. So now going back to the slide to summarize. Einstein notation. It was, in fact, used by Albert Einstein. In some textbooks, when they do derivations of physical chemistry formula, and in fluid mechanics also, they just write Einstein notation. They don't write any other type. It expresses vectors and tensors in Cartesian coordinates as a sum of the basis quantities. We do not write the summation sign. because we use Cartesian coordinates, when we dot various terms together, they become, the dots of the basis vectors become the Kronecker delta, which allow us to simplify. So in order to do it, we write arbitrary indices, but we must always choose new ones. And I'll show you next time the problem everybody always gets wrong when it comes to choosing new ones. And then repeated indices indicate the missing summation sign. Okay, that's it for today, and we'll continue on Wednesday. And I think you have enough to do the homework now.